the assumption. This assumption, I've put it in the appendix of this presentation. We can look at it later. I personally did not understand its significance. That's why I mentioned we'll be learning together. So I'll put it up at the end of the presentation. We can discuss why it's important. And then if those two things are satisfied, then Wasserstein is continuous everywhere and differentiable almost everywhere. So again, I think we saw that problem before. We're at 0 where we're not differentiable really. And statements 1 and 2 are false for the Jensen-Shannon divergence and all the KLs. So we can already see how better EM or Wasserstein is when we are dealing with neural nets that depend on gradient descent, right? We need them to be differentiable and continuous, but 1 and 2 are not really true for JS or KL. Additionally, the paper proves that with a mathematical approach that KL, JS, and TV are not sensible cost functions when we're dealing with low dimensional manifolds, which are pretty common for the problems that we face. And again, we just saw a simplistic example of that as well. Okay, so this mentions here this Lipschitz. So let's look at what that is. So for a function to be Lipschitz continuous, there should exist a positive real k such that the difference between the function values at 2 points is smaller than k multiplied by the difference between the 2 points. And you can already see that that's kind of related to the slope of the function or of the plot that you have. For example, if you move this to this side, then you can see that it's like bound on the slope or on the gradients. Again, this was the intuition that I got, but again, this requirement for this to be Lipschitz and why it's important, I personally did not get a very intuitive understanding of that. And again, I've put that in the discussion for this presentation, and we can discuss that so that I can learn as well. Okay, so if you remember the formula that I showed for Earth Mover or Wasserstein, it is highly intractable because if you remember, I mentioned that we have to look at every transport algorithm or every joint probability distribution between PR and PG, and then find the one with the minimum distance needed. And that's very clearly not tractable. So this paper also shows that the same thing can be achieved by the formula shown here, where we have Lipschitz functions with k being 1. And if you have the expected value of f of x with samples coming from the real distribution and minus samples coming from the generator distribution, then we get the Wasserstein distance here. And we'll see what f actually is and why it's important in a bit. And then if f is not 1 Lipschitz, if it's like, for example, 5 Lipschitz, then we would just get 5 times the Wasserstein distance. And in our case, we don't really care about the exact value of the distance, right? We need it to optimize our model. So it doesn't really matter that we are getting something times the Wasserstein. So it's okay if it's not 1 Lipschitz in our case. And to approximate this using neural networks, we can parameterize f with this with some weights that we have, and then maximize this whole expression. And here f, well, you could see some similarity between this and the GANs, right? So we have this data coming from the real distribution, data coming from the generator's distribution. But if you remember, here we had 1 minus the discriminator, and f is not a discriminator. And this in the paper is called a critic. And the goal of f is not to tell you what data is real and what data is fake. It's to make a good approximation to the Wasserstein distance. So it's not it can be called a discriminator. It's a critic, and it tries to approximate Wasserstein as best as it can. And here in this formula, f can be K Lipschitz. As I mentioned, that doesn't really matter because we don't care about the exact value of Wasserstein. And the problem, okay, let's see if there are any questions. Okay, yeah. So now the question becomes, how do we make sure that these Fs are K Lipschitz? How can we ensure that F is Lipschitz? The way that this paper mentions it, it seems very simplistic, but they say that it did work in their case. So they simply clamp the weights of the model to a fixed subset. For example, here from negative 0.01 to 0.01. And as we'll see in the discussion, again, I personally did not. I don't really understand why just clamping the weight to a region would make sure that this is K Lipschitz. Does this have to do with, again, the gradient thing that I mentioned? The function can't, I don't know, have a sudden jump in the gradient. Is the clamping of the weights helping that or not? But again, we can discuss that later. But the paper suggests this method. And again, we'll come back to this in a bit, but just have in mind that they are doing this to ensure that the functions are K Lipschitz. And this is the algorithm here. So I can go over it and you can also look at it yourself. If you look at this inner loop here, that's the loop that if we take, I don't know, make an analogy to GANs, this would be the discriminator loop. But here, it's not a discriminator, it's a critic. And the good thing here is that we can train this to optimality without having the issue that we had with the vanishing gradients of the discriminator. So there, if you trained it all the way to optimality, then you would have no gradient information to actually train the generator with. But here, you actually have that option to train the critic very close to optimality so that it's a good approximation to the Wasserstein distance, and then use that to train your generator. You're not losing that gradient information, at least theoretically, as mentioned in this paper. In practice, I have not used this before, so I'm not sure if it actually achieved this. And yeah, so I've mentioned this at the bottom again. It's not a discriminator, it's a critic to give you the Wasserstein distance. So let's look at some empirical results then. So they actually mentioned that the benefits from their model is twofold. One is they give you a meaningful metric to look at when you're training your generator, your generative model. For GANs, you have this Jensen-Shannon divergence used as the metric. And for example, in this plot, as you keep training your model and you see better and better results at the output, but look at the Jensen-Shannon divergence. It's going up and then just staying there, right? It doesn't tell you when to stop training, or it's not telling you, oh, your model is doing well now. It's not giving you any useful information. But if you look at on the left side, where we have WGAN that uses Wasserstein objective, we can clearly see that it's going down and it's starting to plateau. Maybe that gives us an idea of how well our model is doing. If the training is enough, we can stop training. So it gives you some ideas on how to measure the performance of your model, which is great. And then the second contribution that they mentioned, which we also talked about before, is that GANs are unstable. It's very hard to train them because of the problems that we saw with Jensen-Shannon. But here they are promising stabler training. So at the top, we can see that. So on the right side, we have GAN. On the left side, we have WGAN. And they are both performing well. And that's because a lot of consideration has been taken into account for the architecture used with the generative, with the GAN models to make them work. But if you remove some of those, for example, this is without batch normalization and a constant number of filters at every layer, GAN just failed miserably, but WGAN is still performing well. So you are getting more stable training using WGANs. Okay, and this is an excerpt from the paper itself, And I found it funny that they say it like this: weight clipping is clearly a terrible way to enforce a Lipschitz constraint. So they are saying that this is not really ideal way of doing it, and this can be, I think I think I saw some papers that try to improve this using a gradient approach. I didn't look at that paper, but it was mentioned somewhere. But yeah, this can be maybe a good research direction to improve WGANs even further. And yeah, to some of the things I raised during the presentation. So the main part of the presentation is over. We can now discuss some of those. If you guys have any ideas of why does the function have to be Lipschitz? Maybe I would have known if I looked more deeply into the mathematical approach behind it. Maybe not. Why does constraining the weights to that region actually pushes our network to produce Lipschitz functions? Why is that? That's not clear to me either. And also, this is the assumption they used along with Lipschitz to say that Wasserstein is continuous everywhere and differentiable almost everywhere. And again, why? So let's put that on. If you have any questions, please ask. If you want to discuss these, again, I'll be more than glad to learn from you. Michael, go ahead.
Yeah, thanks for the presentation, Masood. Sorry if I missed this, but from what I've known before, Earth Mover is this optimization problem that's pretty hard to calculate. So I'm wondering, the WGAN loss function, how close is it to the Earth Mover distance?
That's a great point. So here, if you go back to this slide that I have, I mentioned that it is highly intractable, right, to find EM. And they actually, not in the paper, but they mention another guy's name, something duality, I don't remember. And that says that this is equal to that. So now we have these Fs here, and we can approximate them with a neural net, right?
Yeah.
And the good thing here is that we can train F as close as possible to optimality so that we have an accurate approximation to W. And that's happening here in the inner loop to give us a good approximation for the Wasserstein. But yeah, we're not using the original formula because that just doesn't work.
Oh, so that's why you said F, it's more of like a critic than the discriminator.
Exactly. Its goal is to approximate Wasserstein, to make this whole expression give us a good measure of Wasserstein, not to tell us real from bad.
Yeah. Okay, this is really cool.